but otherwise I'll just go on. So this is the idea for the session for today. So the idea is to talk a bit about the Haskell Web Ecosystem, and then talk a bit about type level computations and how you can do this with type families, how you can do this with type classes, and so on. So let's begin by yes, I said talking a bit about Haskell Web Ecosystem. In the book, I describe two technologies. I describe Spock, and then I go and describe Elm, which is a separate language from Haskell. So it's very close, but it has its separate compiler and its separate ecosystem. Well, when I wrote the book, Spock was, I think, a very nice. I still think it's a very nice choice. It follows this idea of having roots, and then you just return stuff from each root. So it's quite simple, and it's, as I said, this is mostly what people expect. There is this other nice thing called servant, and I think if you nowadays go into web in Haskell, I think you will often end up with something like servant. So servant has this nice idea of using the type system to do web development. So I think it also ties together very well these chapters you've been reading, about web programming and type level. So here is the docs. I just want to show you a bit what I mean by using the type system. So here, for example, here, so you define the API. What's the roots you are gonna serve, and what's the things that you're gonna accept, and the things you're gonna catch with a type. So this is a type level thing. And here you can see things that I'll talk later about, like type level strings or type level lists. But essentially, this is telling you, okay, my web server responds to users/list all, and then gives you a list of user as JSON, or at list all/users, and then gives you again a list of user as JSON. And the nice thing about that is that from this description, which is a description of the API, you can either generate a client from it, or something like this. So you just, you have to write some boilerplate, but then from this, you just get a bunch of functions which do all the things to you, all the marshalling, all the unmarshalling, and so on. And what I find more interesting is that it's very nice to write a server for doing this. Essentially, if you have an API, all you need to do is to give a function for each of the roots. So like here, users give you back a list of users. So you just write a function, users, which gives you back a list of users. And then servant takes care of all of this, and all of this is done using type level techniques. So I think it's a very, very cool thing. We go back to the list. So there is also in the front end, I think that Haskell is not so well developed as in the backend. So you can definitely write backend applications, web applications in Haskell in the backend. In the front end, you find several options, and all of them feel a bit hacky. You have something called GHC.js, which is a GHC which compiles to JavaScript, but it lags behind the current version. And actually, to make it work, you need a bit of extra work. So Miso or Reflex actually give you this Nix thing for reproducibility. So well, to get it working, it's a bit harder. But these are the two main options. So if you wanna read or see about Miso, I gave a talk some time ago about how you can use Miso. Reflex uses this functional reactive programming ideas to do this, but this is Haskell, so you are really writing Haskell. And of course, the nice thing is that then you can use all the libraries. So, for example, if you use Miso, you would just use ASON, the JSON library for Haskell to do your JSON visualization. What I see more often anyway, so from the people which I know trying to get these things, is that they don't really use Haskell because it is not so well supported. Then also there is like a bit of mismatch between well, like the JavaScript way of working and Haskell way of working, starting by the fact that Haskell is lazy. So people just look at other languages like Rescript, which is well, it was previously known as Reason. They just changed the name in the summer, and it like an OCaml, but it has JavaScript syntax. So it's that imagine that you are writing Haskell with JavaScript syntax, and you have Elm, which is Haskell syntax, but quite simplified. So for example, it doesn't have type classes, but you have many of the other things. And and well, these are things which I see people using. So Rescript has bindings for React, so you can just use the usual React. And Elm has something called Elm UI, which is quite nice. It also follows this kind of React idea of working. So, oh, I see questions. So, any thoughts about GSOT for backend and Purescript for frontend? Well, I haven't used GSOT myself. Uh, I think that if you asked me these questions before Servant came out, and it's like it's as developed as it's now, I think that GSOT would have been like my go choice for bigger applications. But I just started with Spock and then moved to Servant. So that's mostly what I just use Servant. So GSOT has this. So the main difference I would say between Servant and GSOT is that GSOT doesn't use so many type level techniques, and it has a lot of type safety by using template Haskell, which is essentially you write parts of your web application using some special languages to define roots or to define templates, and then this is compiled to Haskell in well, it's as part of the Haskell compilation, but it's like a small embedded language. Whereas in Servant, you are all the time using type level, so you see the types that are going on in there. So it's because I'm more comfortable with type level than with the fact that these pieces of codes run, then I like Servant more. But GSOT has like everything. So you know you have GSOT forms and GSOT authentication, all of that. So that's also like Servant and GSOT are nowadays like the big players. And Purescript for frontend, yeah. So Purescript is another choice. So it also has a syntax very close to Haskell, and you can think of Purescript as essentially Haskell, which is a strict instead of lazy, and compiles to JavaScript, which makes it easy to interoperate with JavaScript. I haven't used it myself, and I always, but when I've tried it, always had the feeling that all these extra bells and whistles that a language like Haskell brings or Purescript brings might not be worth it for the kind of simple web applications I was developing. So maybe when things grow, uh, uh, this makes sense. But on the other hand, I've seen people very happily using Elm in actual applications. So right now I would just recommend to if you want to introduce this, just start with Elm because it's or Rescript because it's much simpler and people seem quite happy using it. But other than that, I don't have. I think Purescript is also well maintained, so it's also a safe bet. So I don't know if there are more questions about yeah web. Otherwise, I'll just go on with type level computations. Good. So yeah. So I would say that once you start using Haskell, so the first things usually you learn are, you start by learning higher order functions and algebraic data types and pattern matching. Those are like the building blocks of the language and the building blocks of any language in the style of Haskell. And nowadays, many languages support this. And then you often learn about higher rank abstractions, things like functors and monads, and that's often enough to do a lot of Haskell. But if you want to go the next level, you usually start looking at type level computation. So things you can do with types. That's essentially like you can think of it as or that's how I like to think of it. It's like running small programs in the compiler that ensure that your code is correct. And there are, in a very broad sense, there are two ways to do this type level computation. We have type families and we have type classes, and and I've seen questions about what are the relations and how you write one things in the other. So I'll just try to give a very broad overview of how you can use each of these. But the two main things which separate one from the other is that type families are more like functions in the types, whereas classes are more like relations. So they don't really need to have a function. And the other very important thing is that when you have a type family, you don't have associated term level code. So this is just like a type level function, but that's when it ends. Whereas for classes, you can do elaboration. And let me show you an example of what I mean here. So let's I have a model here. What I'm gonna do is I'm going to define, and that's a very common thing to. I'm gonna define my numbers, which is the often to go example. So I'm gonna introduce the 0, and I'm gonna introduce successor. So these are just two types, and the idea is that if I have a type, you can see that they are empty. So these are types without any construct. These are just types. They don't exist anywhere else. I can have the type 1, which is successor of 0. Something like this. By the way, I'm using Visual Studio Code with this Haskell language server, which is quite nice to work with Haskell. So things I can do is, for example, define what adding up two numbers is. So I can do this in two different ways. As I was saying, I can do this by writing a type family or by writing a type class. So one way to do this is when you write a type class, you usually say, well, type family, and then where, and it tells me, oh, there is an illegal type family declaration. So I need to add type families extension. This is the nice thing about this thing. It allows you to have these quick fixes. And then you say 0 plus n is m. Successor m is successor of add and m. So this is a type family you can use. And another way to do this is to have a type class. And when you have a type class, you just you often, so let's let's call this add f because it's the family. So, but when you have a class, you often play this trick of having an extra argument and then a functional dependency. And again, I need to add extensions and more extensions. So, and now essentially everything you would write above here becomes becomes an instance in the type class. So we said that 0 plus m is m. So 0 plus m has result m. And I need more of these extensions. And then I want to add successor of n and m. And then I say this is the successor of r. And then here is a small trick. I need to say, well, this only holds if when I add nmm, I get r. So it also tells me more instances. So this is telling me that if n plus m equals r, then n plus 1 plus m equals r plus 1. So these are the two ways that I introduced the book, and these are the ways in which you often can write things like this. So what is the difference? When would I choose one or the other? So as I said, type families, if you compare with classes, doesn't give you a way to introduce here things. So I could here introduce some operation which depends on how these things change. So for example, let's introduce, again, using the example which most people often use. I'm going to introduce a GADT, generalized algebraic data type, for lists with have n values. So I also need to introduce GADTs. Okay, and then I can say nil is a list with 0 elements, and cons takes a list with n elements and produces a list with 1 element more. So if I want to write something like I want to append 2 lists, I cannot really do this on the type family directly, but you can imagine having a way of appending 2 lists, saying, well, this takes a list of n values and a list of m values, and give me back a list of r values. So as you can see, you can associate information, you can associate operations with type classes, and that's where the great power of using type classes come from doing when you do type level computation, because you can then associate term level computation to it. So then I can write here, well, my append c, well, because I have 0 as the list, this can only be nil, with ys is twice, and you can see that this is well typed. If I go and try to write append c for cons x x's equals whatever, cons x append c x's y's, you can see that this will be wrong because this pattern match is redundant, because it doesn't belong here, because I'm just declaring the part for 0, but well, this belongs here. So now I can write append for my list. Now, actually, in this case, I've been lying a bit, because in this case, I can also write can append with the type family by saying that if I have a list of NA and a list of MA, I have a list of add FNMA. Then I can just write this 2 lines, and this will essentially compile. Good. So I just wanted to show this because it's actually a bit more subtle, and I would say that one of the things about learning type labeling in Haskell is to know when you can use a type family, when you can, and when that's not enough. So often you want to use a type family if you can, because the code just looks better. It's simpler to understand. So if I'm writing an append function over this list, I want to write something like this. However, this is less powerful. So in general, you will end up using this thing a lot. And you can check in I don't know, I'm developing a library at work called Mu Haskell. That's for microservices programming. It is essentially like servant, like this thing of using a type as an API, but for other protocols like gRPC or GraphQL. But the point is that in order to manipulate those types, in many cases, we have to use type classes because we want to do something with these types. So imagine, for example, that I say, okay, depending on the type, I want to serve different types of things. I want to serve JSON, or I want to serve text, or I want to serve something like this. Well, there is some code associated with the fact that you write JSON on that API. So that means you really need to use a type class there. That's the first thing. Now, let's keep on going and try to do a bit more, to play a bit more with this type level computation. So first of all, this has a problem. When this way of encoding this number has a problem. So if I write some stupid, so imagine I write suck of maybe, it's gonna say this is wrong. I don't know if it can be read here, but it says expecting one more argument to maybe. So of course, I mean, if I have a number, a successor should be another number there. But I actually can write something like successor of bool, because here when I'm declaring my data type, I have just successor of something, and bool is a something of the right kind. So if you remember, kinds are the types of types. So that's of course not what we want. Haskell was like this for a long time, and people came with tricks like this. But at some point, I think around 2010 or something like this, somebody said, "Well, that's crazy. We really love this idea of having strong types, but then our types have not so strong kinds. So what can we do to solve this problem?" So people came with this idea, which could be a bit convoluted, but that's how it is. So imagine that I now declare my data type in the usual way. So this is my usual data type. That's a normal one. Okay. Now, of course, all of this breaks. But now I go and add this thing, data kinds. Well, that means you see that everything now compiled. So that's a very weird thing. What happened is that every data type becomes a kind, and every constructor becomes a type. That means that now you have a term 0. So you can write your sum function. So I can actually write something like add term, which takes 2 natural numbers and returns a natural number, and it will essentially be a copy of this thing. So that's So that's adding at the level of terms, but I've also generated this extra thing. But now, very important is that my type 0 actually has the right kind. So if I try to use this stupid thing, it tells me I expected kind nat, but bool has kind star, and star is just the kind of the rest of the usual types in Haskell. So this no longer compiles, and that's what we want. Yeah, you will also see that if I do this, tell me unticked promoted constructor. Let's wait for that for a minute, and let's try to understand what these data kinds are doing. So in Haskell, we often start with terms, things like numbers or strings or things like this. And these terms have types. So one is an int, and list array is a string. And those types have kinds. So string and int have kind start. And if you remember, you have things like maybe which has kind start to start, right? That's how Haskell often works. So when you do data kinds, the following happens. So here, what I am defining if I don't have data kinds is two constructors, 0 and successor. Let's start with 0. And 0 has type nat, and because this nat is a normal type, it has kind star. So by using data kinds, this thing, and they are called promoted data types because they are like promoted to types, you get a new kind, a new type called 0 coming from the 0 there, which has a kind called nat. So the type becomes a kind and the constructor becomes a type. So that's like, and that's how you actually introduce the usual way in which you can do, well, the usual idea of type safety into the kind system. Now, in order to disambiguate things, it can try to do this, but you get a warning because you actually need to put ticks all around so that the compiler doesn't get confused. But most of the times you don't need those, but you will get a warning when you need that. So that's what data kinds do. That's essentially bringing you the idea of kind safety. So this idea of having strong types to one extra level. So because once you start doing this more and more type level, for example, here this type family now has an actual, it almost looks like a function. This nat are not the types, they are kinds, because f is a type family, which means like a function which operates on types. So this nat is actually the kind nat, which has types 0 and sac n, and so on. Just to give you the whole picture, Haskell nowadays is able to promote these constructors with the tick, but you cannot promote the function. So you have to, even though those two things, this add t and this add f, are essentially the same, you need to